In this video, we're going to go over some practice problems from the material covered this week. So we're starting with section 2.6 here. In 2.6, we're looking at function notation. And so we're given two functions, f of x and g of x here. So for part A, we want to evaluate f of -3. So that means we want to figure out the function or the value of this function when x is equal to -3. So we're going to plug that value of -3 into x here, and then we're just going to simplify. -3 times -3 gives us +9, and then adding 4 to that gives us 13. Now for part B here, we're looking at g of 0. So we want to plug in 0 for our x's here. So we're going to get 0 squared plus 4 times 0 plus 1. So in this case, we're just left with 1. So this means the value of our function g of x when x is equal to 0 is equal to 1. All right, let's look at C here. We're going back to our function f of x, and we want to figure out what this function is when x is going to be 2t plus 1. So we're just going to plug that into our function and then simplify. So in this case, this -3 is going to be distributed to everything inside of our parentheses here. So this will give us -6t minus 3 plus 4. And then simplifying this further, this will give us -6t plus 1. All right, now for D here, we're looking at g of x when x is equal to 1 over x. So we're still just going to plug this whole thing into our x values here. So this will be 1 over x squared plus 4 times 1 over x plus 1. And then if we want to simplify this further, this would be 1 over x squared. When we have a fraction like this with an exponent on the outside, this exponent is going to apply to both the numerator and denominator of our fraction. And then we're going to get 4 over x for our second term plus 1 here. So that's as far as we'll simplify this guy. Now for the next example, question 47 here, we're given an equation. We're given x plus 3y is equal to 12. And what we want to do is rewrite it using our function notation and then evaluate that when x is equal to 3. So remember, function notation, if we have f of x, this is just the same thing as y. So if we're given an equation of this form and we want to write it using function notation, what we'll do is we'll solve for this variable y and then just replace it with f of x. So we have x plus 3y is equal to 12, and we're just going to solve for y. So the first thing we'll do is subtract x on both sides. This will give us 3y is equal to 12 minus x. Then to get y completely alone, we're going to divide by 3. And then simplifying this further, and I'm also going to reorder these terms here so that this x term is in the front. This will be -1/3 x, and then 12 over 3 is just going to be 4. So this is our equation solved for y, so this means we can rewrite it with function notation like this here. Now the second part of this question asks us to find this function value when x is equal to 3. So we're just going to plug in 3 for our x value here. Now doing so, this will give us -1 plus 4, which gives us 3 here. So now we're moving on to section 3.1, and we're going to start with this question 14 here. What we want to do is determine whether this given ordered pair here is going to be a solution of this system. So what we're going to do is just plug in our x and y values and make sure it satisfies both of these equations. In order for this to be a solution, it does have to satisfy both of them, not just one. So we have our coordinate 5, 2, so we're just going to plug in those values here for our x and y in both equations. This will give us 10 minus 2 is equal to 8 for our first equation, and this is in fact true. This means 8 is equal to 8. Now I want to do the same thing for the second equation. We have 3x plus 2y is equal to 20, so we're going to plug in our x and y values. Here we're going to have 15 plus 4, and so we'll get 19 is equal to 20. But this is not a true statement. This is going to be a false statement, and this means that this ordered pair is not going to be a solution because it doesn't satisfy both of the equations. So we would say this is not a solution. Now for this next example here, I've already written down the solution just in the interest of time, so this video hopefully doesn't get too long. But what we're doing is we want to solve this system of equations here by graphing. And so I've labeled the equations 1 and 2 here, and so we're just going to graph each one. So for the first equation, we found the x and y intercepts here, and then plotted them, and then drew our line through those points. And then we did the same thing for equation 2 here, and so that's given in green. Now, to solve the system by graphing, we look at where they intersect. That's going to be this point here, 2, 2. That is the common solution for both of these guys. So in this case, the solution to the system of equations would be 2, 2. And then we could plug in these coordinates into our x and y values here, like we did in the last example, just to make sure that it is in fact a solution. So this is how we can solve the system by graphing. Now there are two things to note here. If we were to graph two equations and we end up having the case where we have two parallel lines, so the two lines are never going to intersect, in that case we would have no solution. So I'm going to do a quick sketch of that. If we have two lines that look like this is going to be the case where we have no solutions, and the systems are going to be called inconsistent. We could also have another case where we end up plotting the exact same line actually. Now in this case, we would have infinitely many solutions. And the system of equations in this case would be called consistent. So these are the three different cases that we'll see. And in the next couple examples, we'll figure out how to get the solutions analytically versus graphing. And in those cases, we'll still end up, or in those examples, we'll still end up with three different cases. So either we'll have one solution, we'll have no solutions, or we'll have infinitely many solutions. So anytime we're solving systems of equations here, these are the three cases we'll have. All right, so for the next several examples here, what we're going to be doing is solving these systems of equations, and we're going to do so using the stated method in each question. So for 26 here, we want to solve this system using substitution. Now for substitution, what we want to do is solve for a variable in either one of these equations, and then use that value to plug it into the other equation, so we can get a value for the other variable. So whenever we're doing substitution, it's always a good idea to solve for the variable that has coefficient 1 or -1. That way, when we're solving for that variable, we don't have to divide out and maybe end up with fractions. So what I mean is, what we're going to do is solve for this variable y here, because its coefficient is -1. So we're looking at this equation, and we can easily solve for y. Doing so, we're going to get y is equal to 3x minus 10. If I had chosen to use the second equation here and solve for y, in the last step we'd have to divide both sides by 5 to get y alone, and we'd end up with some fractions here. So that's why we usually like to pick the one that has coefficient 1 or -1. All right, so once we've solved for that variable, what we're going to do is plug it in to our other equation. So we're going to have 2x plus 5 times y, and we know y is 3x minus 10, and this is going to be equal to 1. So we're just plugging this value into our value for y, and then we're going to simplify this. So we're going to end up with 2x plus 15x minus 50 is equal to 1. Now we can combine like terms with our x's here, and then we'll move this 50 over to the other side. So doing so, we're going to get 17x is equal to 51, and then finally dividing by 17 gives us x is equal to 3. So the whole idea here is to rewrite an equation in terms of just one variable instead of two, so that we can easily solve for that variable. Now, once we have a value for this variable, what we can do then is plug it into that x there, and then solve for our second variable. So we know y is going to be equal to 3 times x, and we just said that x was equal to 3 minus 10. So then solving for this, y is going to be equal to negative 1. So what we get here, our solution set, is going to be written this way with our curly braces because we're talking about a set. It's going to be 3 comma negative 1 here. And in this case, this system of equations is going to be dependent. So we found a solution here. Now for this next example, we again want to solve the system of equations here, but now we're going to use elimination. And this method, essentially what we're doing is we are adding or combining these two equations here. And when we do so, we want to get rid of one of our variables. And so when doing so, we're going to have to manipulate these equations in some way so that when we add them together, one of the variables are eliminated. And we're just going to add them using like terms. For example, if we were to add the equations as is, we would have 2x plus 3x. This is going to give us 5x. Then we have minus 5y plus y, so this will give us minus 4y, and so on. And so then we'll add these constants as well. So in this case, when we add these two equations together, though, none of the variables go away. They're not eliminated. So what we're going to do is we're going to multiply both sides of our equation by some factor that'll make one of the variables be eliminated. And notice that if we're trying to eliminate the variables, they also need to be of opposite signs. So if I were to multiply both sides of this second equation here by 5, notice we're going to end up with this new system here. And when we add these guys together, let's look at this. We have 2x plus 15x. This will give us 17x's. And then here we have minus 5y plus 5y. So these guys are going to cancel. And that's what I meant when we need to have opposite signs for the term with the variable we're trying to eliminate. So our y's go away. And so we'll have 17x is going to be equal to 40 plus 11. So this will be 51. And so dividing by 17 on both sides, we're going to get that x is equal to 3. Now, just like in the last example, once we have a value for one variable, we're then just going to plug it into one of our equations. So we're going to plug this x value into the top equation there. So we're going to get 2 times 3 minus 5y is equal to 11. And so now we just want to solve for y. We'll get this here. So this gives us this by subtracting 6 on both sides. And dividing by negative 5 on both sides, we're going to get y is equal to negative 1. So we're actually going to end up with the same solution set as the last example. That's just a coincidence. 3, negative 1 here. So we do have one solution, so these equations are going to be dependent. Now, for this last example here, we again want to solve this system using elimination. So as we saw in the last example, what we're going to do is try to get rid of or eliminate one of the variables. That's our first step. So what I'll do, I can automatically see that I have a minus 14x here and a positive 7x. So if I were to multiply this equation by 2 on both sides, I'm going to get a positive 14x, and so my x's will cancel. So it doesn't matter which variable you choose to eliminate. It's all about choosing the path of least resistance when doing these examples. You could choose to eliminate a different variable and you should end up with the same solution set in the end as long as your arithmetic is correct. So here our equations are going to become, we have 14x plus 4y is going to be equal to 12. And then we still have our second equation here. So now we're just going to add these guys together like we did in the last example. So we have 14x minus 14x, so our x variable is eliminated. But then notice we have plus 4y and minus 4y, so our y variable is also eliminated. So on the left-hand side, we're just going to have 0. Now on the right-hand side, we have positive 12 and minus 12, so we're also going to get 0 on the right-hand side. And notice 0 is equal to 0. This is a true statement, and this will always be true. So in this case, when we're doing elimination and it results in elimination of all the variables. So we're going to always end up with a case like this here. And so in this case, we're going to have infinitely many solutions. All right. So this would be an example where if we were to graph these two equations, we'd end up just graphing the same line here. Something else I wanted to mention also, if we were to end up with a false statement in the end, let's say if we had 0 equal to 12 maybe, that would be a false statement, and in that case we would have no solution, and that would be an example of an inconsistent system. This brings us to section 3.2, where we're again solving a system of linear equations, but in this case we're dealing with 3 equations and 3 unknown variables. In section 3.1, we saw how to do this with just 2 equations and 2 unknowns. Now, for this section, what we're going to do is follow a procedure, and so I definitely recommend looking through the book and watching the videos if you haven't done so already. Now, this procedure involves getting rid of what's called a focus variable, and when doing so, we're going to be left with 2 equations and 2 unknowns. Once we're left with that, we can then solve the system of equations using the methods that we saw in section 3.1. And then once we get our 2 unknown values, we can plug them into an equation here to solve for our focus variable. So we're just going to get right into it. Our focus variable is always going to be one that should have coefficient 1 or negative 1. So in this case, I'm going to choose x to be our focus variable since it has coefficient 1. Now, again, what we want to do is get rid of this focus variable. So we're left with a system of 2 equations and 2 unknowns. And to get rid of this focus variable, we're going to use elimination when we're dealing with a system of 3 equations. So what we'll do then is kind of manipulate this equation here so that when I add it to one of these guys, our variable x is going to be eliminated. So I'm going to pick these 2 equations first. And when I add these 2 guys together, I want x to be eliminated. So in order to do that, I'm first going to multiply this equation here by negative 1, so that when I add it to this equation here, our x's are eliminated. And then just as a side note, the equation with our focus variable, the book calls our working equation. So we're manipulating this top working equation here. Now doing that, I'm going to get negative x minus 3y plus 6z is going to be equal to negative 1. Now I want to add it to our last equation in this system here. Now doing so, these x's are going to cancel, and I'm left with minus y plus 8z is equal to 13. So I'm left with an equation with just 2 unknown values. Now we're going to do this exact same process now with this working equation and this second equation here, so that we end up with a second equation that just has 2 unknown values. So let's do some color coding. We want to add these 2 equations so that the x variable here is going to be eliminated when doing so. So that means we're going to have to manipulate this guy. We're going to multiply it by a negative 2 to achieve this. So this equation is going to become negative 2x plus 6y plus 12z, and we're multiplying negative 2 by 1 on the right hand side. So we're going to get negative 2 here. And then we're going to add this to our second equation in this system here. So 2x minus y plus z is going to give us 7. And then adding these guys together, our x's cancel, which is exactly what we wanted. We're left with, we should end up with, sorry, just checking the signs here. Yes, okay. So when we multiply this here, we have minus 2 times this 3y, so this should be a minus 6y here. Okay, so we're going to end up with minus 7y plus 13z is going to give us 5. So now we have 2 equations with 2 unknown values. So this is going to be our new system of equations here, and then we can solve it using the methods that we saw in section 3.1. So we have this new system here, which we have minus y plus 8z is equal to 13, and minus 7y plus 13z is equal to 5. So now we can just solve this. In this case, I'm going to use substitution. So we always want to solve for the variable that has coefficient 1 or negative 1. So in this case, I'm going to solve this guy for y. So solving this top equation for y, I'm going to get y is equal to 8z minus 13. Then I can plug this value for y directly into this equation here. So I'm going to get minus 7 times 8z minus 13 plus 13z is equal to 5. Now distributing this negative 7 to both terms in here, I'm going to get minus 56z plus 91. We still have these guys here. Now we can combine like terms. We can combine these z's here, and I can subtract 91 on both sides to move it to the right-hand side of this equation. Now doing so, I'm going to get minus 43z is going to be equal to minus 86. And then lastly, just solving for z by dividing by negative 43 on both sides, I'm going to get z is equal to 2. Now remember, we're just solving this exactly like how we saw in section 3.1, now that we just have two unknowns and two equations. So I'm going to take this unknown, or this value for z, and plug it into our equation for y. So z is equal to 2. I'm going to plug that value in for z there. So just plugging z in there, I'm going to get y is equal to 3. Now we've found two of our unknown values, and we have one more. We have this x value, our focus variable, that we need to find. So I'm just going to plug in our values for y and z into this equation here. And notice we're finding a solution to this system, so I could plug it into any of these equations. But we're going to plug it into this equation, x plus 3y minus 6z is equal to 1. So plugging in these values for y and z, what we're going to end up with is x plus 3 times 3 minus 6 times 2 is equal to 1. So this tells us x is equal to 4. Now this tells us our solution set then is going to be given by this here. Our x coordinate is 4, our y coordinate is 3, and our z coordinate is 2. So this is our solution set for this problem. All right, so for this next example here, we again have 3 equations and 3 unknowns, but this one is slightly different, and that's because notice that this first equation here is missing a z variable, this one's missing an x, and this one's missing a y. So we're dealing with the case where some of our variables are missing, and it actually might make it a little bit easier to solve. Now, we're again going to pick a focus variable, and I'm going to pick y. So this means what we want to do is we want to eliminate y and get 2 equations that don't have our y variable, and then solve the system of 2 linear equations, just like we did in the last example. But if I pick y to be my focus variable, notice that we already have one equation that doesn't have the variable y. So that means this process here that we did in the last example, we only need to do it once for one. So I'm going to take our working equation here and multiply it by some factor so that when I add it to this second equation, our variable y is going to be eliminated. So our second equation here, we have 2x plus y is equal to 6. And if I want to eliminate our variable y here with this second equation, notice we have a positive 3 in front of this coefficient y, or as this coefficient for this y variable here. So what I'm going to do to this one is multiply by a negative 3. So we're going to multiply both sides of this equation by a negative 3. Now doing so, I'm going to get negative 6x minus 3y is going to be equal to negative 18. Now I want to add it to this second equation here, use our elimination process to get rid of our variable y. So adding it to this equation here, we have 3y minus 2z is equal to negative 4. I'm writing the equations with spaces here just to emphasize that it's missing an x variable and missing a y here. Also, so that when we add it together, we can easily see that our y variables are going to cancel. So we're left with minus 6x minus 2z is going to be equal to negative 22. So like I said, we only have to do this process once because now we have two equations that don't have our variable y. So we can solve this system of linear equations with just two equations like we've seen in section 3.1. So we have our two equations, 3x minus 5z is equal to negative 7, and minus 6x minus 2z is equal to negative 22. So this is our new system here. And in this case, what we can do again is elimination. So we can add these two guys together to get rid of one of our variables. Now in this case, since we have a minus 6x here and a positive 3, I can easily just multiply the top equation by 2. We're going to end up with 6x minus 10z is equal to negative 14. We're going to add that to our second equation here. Now doing so, our x's are going to cancel, and we're left with minus 12z is equal to 36. Now lastly, we're going to divide by negative 12 on both sides. This gives us z is equal to 3. So now we're going to take this value and we're going to plug it into our equation to solve for y. So we're going to plug it into, let's plug it into this second equation here since this guy only has a y variable, and then we can solve for it. So z is going to be equal to 3, and we're plugging it into this here. So we're going to get 3y minus 2 times z is equal to negative 4. So again, just plugging that z value in. We're going to end up with 3y minus 6 is equal to negative 4. So this means 3y is equal to 2, and finally y is going to be equal to 2/3. Alright, so now we have two of our unknown values. We found values for them, and so we're going to plug them into our equation to solve for x. Now notice I can actually just plug in a y value in this top equation here and solve for x. We don't need z in this case, but we did need to find z to find y, and in the end we do need our solution to contain all three of these coordinate values. So using the top equation here, I'm going to plug in our value for y and then solve for x. So again, just plugging our y into this top equation here. So I'm going to end up with 2x is going to be equal to, I'm going to do 6 minus 2/3, so subtracting 2/3 on both sides of this equation to get x by itself. Now remember, when we're adding or subtracting fractions, they have to have a common denominator. Currently 6 is just 6 over 1. So in order to get a common denominator, I'm going to multiply by a factor of 1. So I'm going to multiply the top and bottom of this guy by something that'll give me a denominator of 3. In that case, that's going to be 3. So I'm going to multiply 6 by 3, that'll give me 18, and then 1 by 3 gives me 3 on the bottom. So now these fractions have a common denominator, I can easily subtract them. I'm going to get 2x is equal to 16 over 3, and then finally getting x by itself. If I were to divide by 2 on both sides, that's the same as multiplying this by 1/2. So I can multiply by 1/2 on both sides to get x by itself. Doing so, x is going to give me 8/3 here. And then lastly, this tells us that our solution set is going to be 8/3 for x, y is 2/3, and we found that z is equal to 3. So that's how we do this when we're dealing with 3 equations and 3 unknowns, and some of our variables are missing. Now for this last example here, we're going to do the same thing. In this case, I'm going to pick x as our focus variable here. So What we're going to do is then use this working equation here to eliminate that variable, and we'll do so with this second equation here. So in order to eliminate our x's by adding these two equations together, I'm going to multiply this first equation by a factor of 2. So I'll be left with 2x plus 8y minus 2z gives us 6. Now I'm going to use the second equation to eliminate our variable x. Now doing so, our x's are going to cancel, but so are our y's and our z's. So on the left-hand side, we're left with 0, and then on the right-hand side, we're also left with 0. So this is a case where we see that this is always going to be true. No matter what our variable values are, we're going to end up with a true statement. Now, notice if you were to do the same thing with this last equation here, so let's say we wanted to eliminate x with these two equations. I would multiply this guy by -3. Doing that, our x's will cancel. Here, I'll get a -12y, so our y's will cancel, and then I'll get a +3z. Our z's will cancel. And then lastly, on this side, I'll get a -9, so our constants will cancel on the left hand, or on the right hand side. So this is an example where we have, again, infinitely many solutions. Now again, just to emphasize that if we were left with a false statement in the end, then that would be a case where we don't have any solution. So our solution set would be empty. All right, so now we're going to look at some problems from section 3.3. And in this section, what we're doing is working with applications. So we're going to work with word problems, and our job is to convert the word problems into a system of linear equations and then solve for the unknown variables. So in this example, we're told that a tennis court is going to be 42 feet longer than it is wide, and it has a perimeter of 228 feet. What we're going to do with that information is find the dimensions of the court. So I have a little sketch here of a tennis court. This is going to be the length and the width of the court. So these are going to be our two variables that we're trying to find. Now, given our pieces of information, we are going to be able to construct a system of equations. The first is that we're told that a tennis court is going to be 42 feet longer than it is wide. So that means its length is going to be 42 feet longer than its width. So 42 plus W is going to be our length. Now our second piece of information here is that it has perimeter of 228 feet. Well, we know that the perimeter, so 228 feet, is going to be equal to length plus width plus length plus width. So we can also write that as 2 times our length plus 2 times our width. So this will be equal to 2L plus 2W. So now we have a system of linear equations, and we're going to solve for our variables using, in this case, we're going to use substitution. And the reason being is because we already have our variable L isolated. So we're just going to plug this value for L into this variable here. Doing so, we're going to get 228 is equal to 2 times L. Okay, so now we're going to simplify and then solve for W. So we get 228 is going to give us, we have 84 plus 2W plus 2W. So we can combine our W's here, and then I can subtract 84 on both sides. Doing so, I'm going to get 144 is equal to 4W, and then finally dividing by 4 on both sides, I'm going to get that the width of this court is going to be 36 feet. Now with this information, I can plug it directly into our first equation and find the length of this court. Doing so, we get that the length of this court is going to be 78 feet. All right, so that's how we do an example like this, and then we can always check our answer by plugging this solution in for our variables and making sure it satisfies both equations. Now for this next example, we're told that at Panera the bill for 2 cappuccinos and 3 cafe lattes is going to be this much, and the bill for 1 cappuccino and 2 cafe lattes is this much. And what we want to do is figure out the cost for each drink. So Again, we're going to write a system of equations and solve for our unknown variables. And our unknown variables is what we're trying to find, and we're trying to find the price for each drink. So what I'm going to do is label. We're going to let our variable C be equal to the price of our cappuccino, and then L be equal to the price of our latte. Now, doing so, we can construct a system of linear equations using these variables with this information. We're told that the bill for 2 cappuccinos, so that'll be 2C, and so we're going to add 3 cafe lattes, so 3L, is going to be equal to $19.75. We're also told that the bill for 1 cappuccino, so that'll just be C, and 2 cafe lattes, so 2L, is going to be $11.97. So now we have this system, and we're going to solve for our variables using the methods that we've discussed in the last several examples. Now, in the last example, we used substitution. So here we're going to use elimination. And you can use substitution if you'd like as well, but I just want to show that there's a couple different ways we can do this. So to use elimination, I want to eliminate this variable C, and I'm going to do that by multiplying this second equation by -2 on both sides. Doing so, our system is going to be this here. We still have this first equation on the top, and then we're going to add this second equation here that we get after multiplying the second equation by -2. So adding these guys together, our variable C is going to be eliminated, and we're left with minus L. It's going to be equal to -419, and then getting L completely alone, we're going to get that the latte is going to be $4.19. Now, with this information, we'll just plug this directly into one of these equations here and then solve for C. In this case, I'm going to plug it into the second equation here. So C is going to be equal to, or C plus 2L, and then L is 419. It's going to be equal to 1197. Okay, so just plugging in this value for L here. Now we're going to get C plus 838 is equal to 1197, and then solving for C by subtracting this 838 on both sides, we're going to get that our cappuccinos are going to be $3.59 each. All right, so that's how we do a problem like this. And lastly, we're going to look at this question here. We're told that the perimeter of a triangle is going to be 56 inches. The longest side measures 4 inches less than the sum of the other two. 3 times the shortest side is 4 inches more than the longest, and we want to find the length of all 3 sides. So the first thing we want to do is assign a variable to each of our unknown quantities. So we have that here on the left. I'm going to let x be the length of our shortest, y middle, and z longest sides of this triangle, and that's represented by this diagram here. So now with this information on the left, what we're going to do is create our system of equations. So the first piece of information is that the perimeter of the triangle is 56 inches. Well, we know that the perimeter of a triangle is just going to be the sum of all 3 sides. So that means x plus y plus z, the perimeter is going to be 56 inches. Next piece of information says that the longest side measures 4 inches less than the sum of the other 2 sides. So the longest side z is going to be 4 inches less than the sum of the other 2 sides. Well, the sum of the other 2 sides would be x plus y, and z is going to be 4 inches less than that. And lastly, we see that 3 times the shortest side, so that'll be 3 times x, is going to be 4 inches more than the longest side. So this would be 4 plus our longest side, z. So this is our system of equations here. Notice we have 3 equations and 3 unknowns. Now, before we get started on finding a focus variable, eliminating it, and solving for these unknown values, I'm going to rewrite this system so that all of the equations are in standard form. Remember, standard form is ax plus by is equal to c, where a and b are some numbers not equal to 0. And just so we can easily see what's going on, when we have the system of 3 equations here, remember we're using elimination to get rid of our variables. And if we're adding them together like this, it looks kind of goofy. It's not very easy to see what's going on. So we're just going to rewrite it. the first equation is already in standard form here. Now the second equation is not in standard form. And actually, just to emphasize here, this is the same thing as just x plus y minus 4. I just wrote this sum here in parentheses because of the way the information was provided. So it can be rewritten like this. So in standard form, this constant's going to want to be on the other side, and all of our variables are going to want to be on this side. So I'm going to subtract z and then add 4 on both sides. So doing that, I'm going to get x plus y minus z is equal to positive 4. And then for this last equation here, again, we want our variables to be on one side, so I'm going to subtract z on both sides. I'll get 3x minus z is equal to 4. So this becomes our system of linear equations here. We have 3 equations and 3 unknowns. So this is going to be similar to the second example we looked at for 3 equations and 3 unknowns when one or more of the variables are missing. So here, in this last equation, our variable y is missing. So in that case, we're going to let y be equal to our focus variable, because remember, we're trying to eliminate the focus variable for 2 equations and then turn this problem into a linear system of 2 equations and solve using the methods we saw in section 3.1. So the whole idea is to reduce this to 2 equations by getting rid of our focus variable in 2 of these 3 equations. This first equation, we're already rid of the focus variable, so that's one of them that we're going to work with. Now to get rid of the focus variable in another equation, we're going to work with these 2. So let's do some color coding here. I want to get rid of y, so I'm just going to multiply this one by -1, so I have minus y plus y, and these guys will be eliminated. So I'm going to multiply the top equation by -1 on both sides. Now doing that, I'll get this here. And then I'm going to add it to this second equation so that our y's can be eliminated. So doing that, our y's are eliminated, but notice so are our x variables. Now that's fine, this actually makes this a little bit easier for us. We have minus 2z on the left-hand side, and then minus 52 on the right-hand side. Dividing by -2 on both sides, this will give us 26. Now, usually when using this method, when we do this process, we would end up with another equation that doesn't have this variable y. We could use that equation along with this one to solve for one of the other variables. But in this case, we actually just ended up with one of the unknown values. So we don't have to do the next step in that process where we work with 2 equations and 2 unknowns to find the unknown values. So now we can just plug in this value z into this equation, because here we only have one unknown value, x. So plugging this z in will give us our x. So we have 3x minus z is equal to 4. So just to emphasize, we're plugging in this z value here. So we're going to get 3x is equal to 30 by adding 26 on both sides. So the length of our smallest side is going to be 10. So now we have the length of our smallest side and our largest side, so we can just plug them directly into one of these equations here and then solve for our middle side. So doing that, we're going to use the second equation. We're going to plug in 10 for x and 26 for z. This gives us y minus 16 is equal to 4, and so y, the length of our middle side of this triangle, is going to be 20. So that's how we would do an example like this when we're dealing with 3 equations, 3 unknowns, and then with one of the equations missing one of the values.